Alright, this is our final video lesson in the gas unit. Right now we're going to take a look at Dalton's law of partial pressures. So far everything, all the lessons have culminated to this point where we can start to take a look at what's happening to specific gases when we combine them in a container. So when Dalton was doing his experiments, he was doing experiments with different gases in a lab, and he was experimenting with water vapor, sort of by accident, water vapor mixing in with the gases. He wondered if it was possible to isolate one gas in a mixture, isolate certain properties of that gas. And we can remember that 1 mole of any gas will have the same volume when the temperature and pressure are constant. When we add non-reacting gases, they will have the same molar volume as a pure gas. So if you had, say, just oxygen gas and you had a mole of that, and then you stuck a mole of, say, water vapor inside the container, they would still occupy the same volume. However, if we go back to the kinetic molecular theory, we understand that the particles inside, even though they're not taking up greater volume, would be interacting more with each other, and there would be more interactions or collisions with the container wall. And this is what we call pressure. So John Dalton discovered a way to describe the pressure of one particular type of gas when it's mixed with others. So an example here is Dalton put some oxygen gas into a sealed cylinder, measured the pressure at 45 kilopascals. We are representing the oxygen gas by these little pink dots here, and they represent the particles. And of course, the particles would be moving in straight lines, zipping around, bouncing off the container. And every time they collide with the container, adding pressure to it. Now, let's take the same number of oxygen particles, put them in the same container, but let's add some water vapor to it. Dalton noticed that the pressure went up. And so it turns out that both gases are adding pressure to the container, and it's a cumulative pressure. So what did Dalton conclude? That obviously the two gases added more pressure to the container. So adding more gases to a container increases the pressure, and from this Dalton was able to develop his law of partial pressures. In a mixture of gases that do not react chemically, the total pressure is the sum of the partial pressures of each gas. So if we were to go back and take a look at the pressure here in this container, it would be equal to the pressure of the oxygen gas plus the pressure of the water vapor. And from this, we could actually determine the pressure of the water vapor pretty easily, because we know that the pressure in this fictitious case is 78 kPa of the entire mixture. We know the pressure of the oxygen by itself is 45 kPa. And then we could determine then the pressure of the water vapor. And we would get 33 kPa. And so we could determine, even though we have mixtures, we can determine the pressure of each gas. And this can become useful when you are working in standard conditions. You can determine, or you can identify, if you have a mixture of gases, what the pressure of a specific gas would normally be at that temperature and pressure, and then you can isolate it out from the total pressure and determine pressures of other gases involved. So let's go back to Dalton's law of partial pressures. So we'll just quickly explain why this is happening. The two separate gases, when two separate gases are originally at the same temperature are mixed, the temperature and thus the average speed of the gases does not change. So by adding more gases in here, they may collide with each other, but they're not going to speed up. Only the total number of molecules in the container increases. Therefore, there are more molecules colliding with the walls of the container, and this makes the pressure increase. Now, how does this apply to how does this apply to gas stoichiometry and the ideal gas law? Well, many gaseous products of a chemical reaction collected over water in the laboratory. So you now have water vapor mixing in. To use the ideal gas law for any gas collected over water, you need to subtract the partial pressure of the water from the new pressure of the gas created. Otherwise, if you go to make yours, they will they will be off because you've got the added pressure of the water vapor. And chemists have determined set standards of what pressure water vapor would give at certain pressures. So to find out the partial pressure of the dry gas, say, you would subtract the pressure of the water vapor from the total pressure. Kind of like what we did up here. We identified the total gas and was 78 kPa. We know that this was from the oxygen gas and the water vapor. In this case, what we actually determined was the pressure of the water vapor. In the case of doing a total pressure gas produced, you would go to a chart and determine at that temperature what the pressure of the water would be, and then you would subtract that from the total to give you the dry gas. What we're going to do right now is take a look at stoichiometric questions, and we'll see. We'll go through and use the ideal gas law here. So the first problem we have is, what volume of hydrogen gas is produced when excess sulfuric acid reacts with 40 grams of iron at 18 degrees Celsius and 100.3 kPa? So we're just going to do some gas stoichiometry right now. So what we do, of course, is we write down what's been given to us. We know the mass of the iron is 40.0 grams. We know the temperature that we're dealing with is 18 degrees Celsius. Now let's quickly convert that to Kelvin. So we take our 18 and we add it to 273 and we get 291 Kelvin. Our pressure is 100.3 kPa. We don't need to change that. But in order to get mass to moles, which is what we'll need to use in the ideal gas law, we need to go and look up the molar mass of iron, which is 55.85 grams per mole. Now, our next step is to write out the chemical equation. So we have elemental iron reacting with sulfuric acid, and that is going to produce our hydrogen gas, and some iron 2 sulfate. And that, of course, will be left in solution. So again, with these questions, we do the stoichiometry. We write it out, write out the chemical equation. So we need to determine the moles of iron. So N equals M over MM, mass over molar mass. We know our mass is 40 grams. Our molar mass is 55.85. So we know we're going to have close to a mole, but not quite. So we're going to have 0.716 moles. So now we can if we know our number of moles of iron, we can determine if we've got the chemical equation balanced, which we do, we can determine the number of moles of hydrogen gas. So in this case, it's a 1-to-1 ratio. So because it's a 1-to-1 ratio, we know that our number of moles, N, is 0.716 moles. Alright. Now our next step is to substitute, or is to determine what we're looking for. So in this case, we want to determine the volume. So volume is going to be nRT divided by P. And what I did, I'll just show you here at the side. Ideal gas law, PV equals nRT. Alright, we want to solve for V. And so in order to do that, we divide both sides by P. Choink, choink. There we go. So we'll quickly substitute everything in. 0.716 moles times 8.314 kPa liters over mole Kelvin times our temperature, which is 291 Kelvin. Divide all this by our pressure, which is 100.3 kPa. And we get 17.3 liters. Okay, at this point, what I've done is put out a couple more questions that deal with the ideal gas law. So some more practice with that. I would take this time to quickly write out the questions, pause it perhaps, write the questions out, and then I'll take you through the solutions. Okay, so the first question looks at what volume of hydrogen gas would be produced at 93.0 kPa and 23 degrees Celsius from the reaction of 33 milligrams of magnesium with hydrochloric acid. So, well, first order of business, of course, is to write out the chemical equation. So in this case, and make sure that we balance it. So we've got magnesium reacting with hydrochloric acid, making our hydrogen gas and our magnesium chloride. So we know some information about the magnesium right off the bat. We know it's 33 milligrams, so we convert that to grams. Find the molar mass, 24.31 grams per mole. Determine the number of moles. Now we look at the molar ratio between magnesium and hydrogen, and we see that it is a 1-to-1 ratio. So by doing that, by seeing that, we can then go and solve for the rest of the stoichiometry. So we know our number of moles would be the same. We know what our temperature is from the question. We know what our pressure is from the question. And so we want to solve for volume. So we just write out the formula, manipulate it, plug everything in, and we get 0.36 liters. Now for the next question, we're asked what mass of oxygen gas reacts with hydrogen gas to produce 0.62 liters of water vapor at 100 degrees Celsius and 101.3 kPa. So we write out the chemical equation. We determine what's been given to us. We know that in terms of our water vapor, our volume of water is 0.62 liters. We know the temperature is 100 degrees Celsius, and we know that our pressure is 101.3 kPa. So we're trying to find number of moles here. That's the missing variable. We solve for a number of moles, we get 0.020 moles of water produced. So we know that the molar ratio between the water vapor and the oxygen is 2 to 1. So that means there'll be half the number of there is. So we do that at number of moles, we find our molar mass, and then we find our mass by taking our number of moles, multiplying it by molar mass, and we get 0.32 grams. So that's how much oxygen would need to react with the hydrogen gas to produce that much water vapor. This ends the series. I'll be posting a couple more videos that show more examples of using Dalton's partial pressures and some more questions, trickier questions that you'll need for the unit test and the exam.